Welcome back to Let's Design Factorio, where we are going to be working on nuclear power. And there's been a few changes in the way things work in 2.0. One of the things that's notable is that, if I remember correctly, when water is boiled into steam, it creates a lot more steam quantity-wise than it used to. So it doesn't use up as much water. It used to be really, really difficult to supply water to nuclear power plants, but I think now that might be different. So here we have steam at 1,000 degrees. And I want to test out to see how this works. Thing is, I have to consume the power. Electric energy interface? Whoops. See, that's not doing what I expected. Oh wait, electrified floor. Turn that off. That didn't help. Power usage. Ooh, here we go. Power production. Ah, nice. That's how it works. I get it. Okay. This is producing 5.8 megawatts. And its consumption is 3.6 or 36, yeah, 3,600 per minute. 3,600 steam per minute. So what we'll do is we'll copy. Oh no, that's not going to work. So you'd think a Factoriopedia would give you, useful tips about things like what's the flow rate on the pipe. I think it's still 1,200 per second, which is 72,000 per minute, which is 20 of these steam turbines. So in theory, this won't go at full speed. Is it really 86,000? 86,400. What's that? That's 1,440 per second. I thought it was 1,200 per second. 1,440. Hold on. So that's 24. So they're all going at full speed. Is that possible? All right, well, let's push our limit. And in theory, this would be way too many. Oh my gosh. 259,200. What? Something that is very odd is happening. No. It just keeps going up. Is there... It seems broken. There should be limits on the pipe. Well, this is 12,000 per second. That seems a bit high. 978 megawatts. Yeah. Yeah, well, they're all going. I don't get it. $248 turbines. You know, I'm very confused. 496 turbines. 2.9 gigawatts roughly, which is what we got. What, is there no limit on steam through a pipe? What's going on? Very weird. All right, well, that wasn't what I expected. Let's disconnect this for a bit. If I can see it. And they all went silent. Okay, so unexpected. What can we do? What can we do? What can we do to make sure that that's how it will work in the game? I mean, maybe it's broken here. Maybe something's gone wrong. Because I don't see how we can do 496. That's a ridiculous amount of like air fluids. That was 1.8 million per minute. There's no way. That's 30,000 per second. There's no way. I mean, unless I'm wrong. So, all right. So what are we going to do? What are we going to do? We're going to test heat pipes and nuclear reactors. Let's set up a pretty basic nuclear reactor grid. 12 reactors. Heat pipe. So heat pipe, we're going to surround. Can I surround the whole thing with heat pipe? Maybe, because we've still got to get fuel into them, right? And out of them. Well, here, let's. It's difficult to know how to, like, where to sacrifice your inputs. I think I can go. I want to put an active provider and definitely a requester, which means, because what the active providers do is they will provide whatever you dump into them into the network aggressively. So they will not store it unless there's no place to put it in the network. So bots will come and pick it up always and stick it in some storage box someplace. And you want that because you don't want these to fill up. That's really important. The question is, can I just do this over and over again? Yeah, maybe that. Okay, that looks like the right way to do it. It does. It looks like the right way to do it. So we gotta get rid of these. Don't need those. And this is going to request a fuel cell. Probably two of them. Well, one of them. Because the bots will always bring more. So they'll probably drop off 4 at a time. So we'll just put that in all of these. There we go. Right. And doubling up on the heat pipes is more of a throughput thing to make sure your heat gets out. Although they are expensive, so this is going to be a pricey build. I think they are. Hang on, let me just check. Oh gosh, yeah, 20 copper and 10 steel plate per unit, and I've got 232 heat pipes just in that part. So this should be a very, very efficient providing of heat. Then we want to get the heat into heat exchangers. Is it exchangers or? Yeah, heat exchangers. So heat exchangers connected to the heat pipes. And these will take water in, like ordinary water, and they will pump out steam. Now, let's go over here and just put it into this ridiculous thing, and we'll see how much power we actually get from it. And that means we need to put down roboports. And oh crap, they don't reach. All right, well then it's going to have to be substations. Of course, there is a problem with this idea, and that's the sense that if the power goes out, there's nothing to feed the cells back in. So we should not electrify the floor, but actually provide power by solar panels. Probably just a small number of them. Maybe an accumulator. Okay. So this is just to power the inserters and the roboport. The roboport is going to be in, you know, like right here. I wonder how much electricity. 2.1 megawatts, really? Minimum. Wait. Oh boy. Well, I don't want to power the. Well, yeah. It's a tough one because I'm delivering by bot. Yeah, so this is going to provide uranium fuel cells. Yeah, so this will be the source of those, and then there's going to be a roboport here, and we're going to put a requester chest here for the spent fuel cells. And that's just going to dump them into, you know, just get rid of them. We'll deal with that later. At this point, I just need to put some bots in the scene, and they should take care of powering the reactor. Now they're going slowly because that's all they've got is a little bit of power from the solar panels. But then this is heating up, right? Because the nuclear reaction is going now. Looks like it takes a while to heat up too. So how many I got? 10? All 10 of them are running. And this is the fuel cell getting used up. And this bar, this red bar, is the temperature of the system, the temperature of the reactor. So it's at 200 and climbing. And that heat is getting transferred to here, where the water is coming in, and we're having steam that should start coming out, generate steam at 500. So as soon as this reaches 500 degrees, it's going to generate steam and stick that out this pipe here. And then we'll just use that up. And measure how much we've used. Because this is separate. This is separate. All right, here we go. Now we're generating steam, and the temperature continues to climb. And the steam is coming through here, and starting to get used up by these turbines, we should be able to measure. So steam production is 6,200 per minute, and the consumption is matching it. So that's how much we can make per heat exchanger, 6,200. So if I cut this and just have one, now what we should see is 3,600 per minute, which looks to be about exactly half of what it produces. So if I put another one on here, so they've used up their first fuel cells, I guess. We can look at our fluids. We can see that consumption is, or production and consumption is both 6,000. Well, actually, wait, 7,200. Hold on. Oh, come on. You're telling me consumes steam 60 per second, consumes water 10.3 per second, generates steam 103 per second. Oh, wow. Oh, wow. So 103 per second is 6,180, which is pretty close to what I thought I was measuring. So it's actually, yeah, 6,180 is the true amount. But these are using it up at a rate of 60 per second, but mine says 52.1 of 60. I wonder what that means. Why would I be only... Oh, right. So that's because two of these can consume slightly more than one of these can produce. So if I really wanted to... yeah, this is... So now it's 1,000. It's 1,000 degrees, which is going to be your optimal temperature. Max consumption, 10 megawatts. Output 103. What happens if I put another one here? And now I'm producing 206, right? 206? And I'm consuming 120. So this should be 12,360. And this should be 7,200 even, which it looks like it is. Yeah, okay. So the numbers are working, and that's what I needed to verify. So then the next question is, how much heat can I actually use from this setup? And that's going to be the magic number to figure out. So there's 12. Well, that's interesting. It's producing 120 megawatts. Exactly. Like, very reliably. So 120, 12, and I've got 12. And each one, it says max consumption 10 megawatts. So that makes sense, actually. So that will... They're actually making 10 megawatts each, these guys, worth of steam, which is measured now, verified through this monstrosity. But the question is, how much am I actually producing? We know that these have constant 40 megawatts each. And then they have a neighbor bonus of 40 megawatts. So this is 40 plus another 80 is 120. So if the corner ones have 180 or 120. And then there's another one for the side ones, which have, so they would have 160, which means it's 120 times 4 is 480 total for the corners. And then each of the side ones, which are 6 times 160 is 960. 960 plus 480 is 1,440. So it's 1.44 gigawatts, which means that I need 144 heat exchangers to actually bleed off all of the heat that this is producing. And that's actually a lot. That's a lot. And the question is, how much water does it consume? Consumes water 10.3. Not that much, actually. So times 10.3 per second. That's 1,483 water per second. Well, so I need to do 144 heat exchangers. So we have to figure out how far, yeah. Let's delete this. Okay, so that's 24. It's 24. It's amazing how fast it is because of the new pipe mechanics. It's just, bam, it's 240. No sloshing, no anything. So if this is 2 dozen, and I need 12 dozen, then I need 6 of these, and that's 144. So, okay. Alright, alright. Let's find out how to optimize this a bit. And that's brought us up to 300, which is not what I expected. Temperature's down. $480. That is what I expected. So if for some reason it took a little while to creep up, but it eventually got to 480, which is what we expect. So that's 4 dozen. Now, question is, should I put them up here and down here? I could. I might. I'd like to make it look good. I would. And to do that, all right. Well, what we should let's measure. Let's measure things. What's nice? 960, which is top. Top is 960 is what it should be. Oh, it sure is nice having the new pipes. I'll tell you that much. Now, this might stretch the limits of how much water we can supply. Now it's climbing. Climbing once more. But I suspect it's capped out because of the water. Fluids, water consumption. And what we've got here is 69. Oh, wait. Now it's going up. Look at that, 1.2 gigawatts. I don't understand why the water consumption count is climbing so much. It's a bit strange. Look at that, it's almost 90. What is 90? 90,000 divided by 60 is 1,500 per second. And that shouldn't be possible. Oh, now it's 89,072. 1484. I think that's what I calculated it would be. 1484. Right? Because these say consumes 10.3. Divided by 10.3 is 144 even. So that's exactly right. So that means it's stable. It's actually producing, you know, and there it is, 1.4 gigawatts. Wow. So from one water pipe, and one steam pipe, we're effectively running a 10 reactor power plant. Now, here, let's just check. Uranium fuel cells. It says 3 per minute. 3 per minute. So as long as I can provide 3 uranium fuel cells per minute, I can run this reactor nonstop and produce that much power. Now, it's worth noting that a solar panel outputs 60 kilowatts. And that means that, if my numbers are correct, that this reactor setup here produces as much electricity as 24,000 solar panels. 24,000 solar panels. That's just mad. And you saw me design it. It wasn't that bad. It's a pretty solid setup. I mean, one can hope that it's as long as this electric network stays isolated from the outside electric network. Like even this is isolated, but it doesn't have to be. I just was measuring. Yeah, but 1.4 gigawatts. That's really pretty good. Pretty good. And so now the thing that we have to do is we have to figure out how many of these is 1.44 gigawatts. And it says power output 5.8 megawatts. Well, hang on. Let's do this one more time. We're going to cut. So now this is running full speed. Consumption 60 per second. Production 10.3 per second. 10.3 times 144 is 1483 divided by 60. No, this is 103. So 100. Hang on. 103 times 144. 14,832 steam divided by 60 is 247 of these guys. Or if I calculate a different way, it's 1440 megawatts divided by 5.8, which is 248. So we'll round it up to 250 to be safe. So now we'll take this off and we'll replace these. And how many do we have? We have 496, which is far too many. Funny enough, this is almost exactly half, just by chance, it's almost exactly half of what it should be. And so let's delete all of these. And then we'll count the remainder. Which is... wait. 248. So I really needed 2 more. I mean, well, technically I think this is actually this actually is the... I don't know how that happened. I honestly don't know, because I was putting these down just out of sheer, incredulity at how much I could fit on this line. And when I decided to stop and double the line and come back, I actually, by chance, had created the exact number of turbines that I need. So why don't we... Question is, can I pass these through? Can I make this a little bit better? Yeah. All right, let's take these. We'll copy them like so, and then we'll duplicate that like so. That's 64, 128, 256, which we don't need 256, remember, because that's 248, which is the magic number. That's what we want. So this setup, I'm going to make a blueprint. Let's make a book called Nuclear. And we'll put this one in, and we're just going to call this turbines, because that's the number of turbines to put in for this reactor, for this this power plant. Save blueprint. Then we will take no, I can't do that. What we'll do is, well, let's move this further in. We want to make it as tight as we can, right? I can't help but wonder if I can do a little bit better job. I know one way I can do this better. Here, hang on a second. I got an idea. Let's take this. We'll put it up here. We'll delete this. Then we'll cut that and paste it there. We will move these heat exchangers here, like that, and then the water all right. Yep, let's do this on both sides. I like this. This is a nice design. Let's get this water source out of the way here. Put it somewhere where it's more likely to be. There we go. Oh, isn't that much better? Isn't that much better looking? In fact, here, let's move these a little bit. Put them here. Make this a straight pipe through. Maybe put them back here like that. Oh yeah. Yeah. Okay, I like this a lot. I might even be able to make it slightly more trim by sticking that in like this, and then putting the underground pipe here, and then here. It's pretty much. I wonder why this is empty. No power. Excuse me? There's a solar panel right there, guys. Why is it trying to use 5.3 megawatts? Is it because of this? It is. The roboport's drawing the power. Dang, man. Well, here's the solution to that. We'll put the, well, actually, there's no solution to that. That's... Roboport draws 470k. Now it's drawing 170k. Ah. Why does it say it wants 5.3? That's so weird. Okay, well, regardless of the roboport, the main thing is that I've got a pretty solid nuclear power blueprint. In fact, I could probably tighten it up slightly more. Yeah, you know what? I actually could. I got an idea. Because there's no real reason not to have... here. These can just overlap. And then over here... like that. But to make things even cooler, why don't we shift the entire thing over so that it's centered like that? Oh man. There we go. That's pretty daring and pretty crazy, but pretty awesome. Here we go. I got another way to innovate a little bit. Let's move these slightly that way. We'll take the water pipe and we'll run it through this way, so we don't have to run it through this way. And then we'll run the steam pipe up. Where's my undergrounds? There we go. We'll run the steam pipe like so, right? Maybe we can move these solars over here, and then we'll just delete everything on this end and replace it with a mirror of what we got on this end, like that. Oh wow, that's incredible. Now, then we'll take this, connect them in the middle like so, which is very badass and very compact. That's really super cool. Super cool. Man. I didn't expect to be designing a really cool power plant like this, but I'm pretty happy with it. I do wish I understood what was going on with these, but here, let's add some more solars. Well, according to this, yeah, I mean, it's 840k, but it wants 5.1 megawatts for some reason. It says max consumption 2.1 megawatts for the roboport. Well, then I sure would like to know what the 5.1 is meant to be. It's so weird. Why is it doing it? I don't know. Can't explain. Anything else I can do to optimize this thing? Let's make some counts here. What do we got? So we go into the nuclear thing and we're going to save. Let's see what we got. Power plant needs 248 turbines. Cool. All right. So look, 676 heat pipes, which is a lot. Admittedly, that's a hell of a lot. 144 heat exchangers, 10 nuclear reactors, and everything else is... Oh, let's get rid of that. Let's get rid of that because we don't want that in the blueprint. Again. Yeah, so the water comes in here. Steam comes out here. Let's get rid of these guys as well. That's just incredible. So the next thing I need is to reprocess the fuel, the spent fuel. So rather than dumping into here, we're gonna let's put down using nuclear fuel reprocessing recipe made in the centrifuge. So what do we get out of it? We get U-238. Wait, what? Oh, no. Yeah, that's it. So, oh, that's rather lame. So for 5 depleted uranium fuel cells, you get 3 ordinary U-238. Okay. And how long does it take? Like here, let's give myself some of the depleted stuff. Where is it? Well, hey, no. We can just measure it here. So 5 per minute. Oh, so only one of these can do 5 per minute. And I'm only using 3 per minute, so I don't need any big elaborate setup. Well, that means it's just going to be a requester and a provider chest. So this is going to be a requester chest, and it's going to request the depleted cell, right? It's going to put it in there, and then what's going to come out of here is going to be pushed into an active provider chest because we don't want to back it up, and then that'll get stuck into storage someplace. I wonder what happens if you put productivity modules into it. Oh, I'm not going to worry about that in the game. I'm not going to do it in the blueprint. So the blueprint is fuel reprocessing, which is this guy. Great. Well, that's super easy. And the next thing we really want to do, and which is going to be a big deal, a very big deal, is we want Kovarex, Kovarex processing. Kovarex enrichment process. And that uses 41 of the good stuff to give, or fuses 40 of the good stuff to give you 41. I wonder if I could, there's a lot of people who've come up with designs for how to figure out the best way to do Kovarex. See, the problem is that you can put U-235, where is it? I'm just going to need to stick it in here then, fine. That and that. Okay, so let's give myself 100 of each, and I'll show you what's going on. So what's going on is if I put 100 of each in here, it's going to use 40 from this one and 5 from this side. And you can see how it takes a really long time. But the problem is that it's got 60 left in here. And that could be used somewhere else. So when you don't have much of this to go around, you want to take your output 41 and dump it right back into the input, but you don't want to put more than 40 into this thing. And so I think what I'm going to do is, first of all, read contents. Oh, wow. So it says 100 and 100. Now it says 101 and 97. So it reads the input and the output together. Okay. I get. So let's think about this. Oh, read ingredients. Read recipe finished. Read ingredients. So if I put 6 in, what does this mean? 40 and 5. 40 and 5. That's read ingredients. Wait, outputs the ingredients required for the currently configured. Oh, outputs the given signal for 1 tick when the recipe completes. Read working. Outputs the signal if the machine is working. So read ingredients sets the recipe from the first valid recipe. No. This is read contents. Let's untick that. Okay, so now it says 40 and 5. If I put an extra 3 in there, it still says 40 and 5. But if I check this as well, it says 43 and 5, which is a bit weird. So it's like, this is how much we want plus how much we got. I'd like to subtract it rather than add it, but I don't know if there's a way to do that. Read contents. So the input and the output. Yep, the input and the output. Okay, I got an idea. We're going to put a condition on this inserter. There's going to be 2 inserters. There's going to be. This is tricky. It is, but I'm pretty sure something can be done with this. Okay, I think I get it. This side, on the input, we're going to put a circuit here. And this has got 3, but we know it wants 40. So we're only going to activate this when green is less than 40. And I'm going to have a requester chest here that wants no. No, I don't want it in one of those. I want it in an underground belt. So this will dump. This is going to filter just the U235. So if you think about it, if this is less than 40, if it's less than 40, this will run to put more in. And this is just going to filter to take it all out. But I'm thinking of also reading the belt contents of the belt. Cannot connect to wire. Seriously? Oh, really? Hold all belts. Belts are cut on side loading and on side loading and inside of splitters. So read belt context. So it says it's got 3, which means this will work, and then this will dump into there. Maybe I want to put that on this side, because then, see, now it says 3. Read hand contents. Oh, okay. So that means... Oh, no, no, no. I'm going to disable this unless this is greater than equal to... Oh, okay. No, greater than 40, which means that if it's not greater than 40, it's going to be stopped, and then nothing will ever get inside this thing. And then this will go into like the provider chest. And this should be overflow in theory, because if I feed all of these in, now this will run. As you can see, it's running because it has more than 40. It has 61, which is this 61. But if it's only got 5, this is not running, and this is enabled. Boy, that could work. It could work. All right, what we have to do is we have to try it, and this time we also have to handle the U-238. So we'll set that filter up here, because this will actually use it up, because the recipe takes 5 U-238 and returns 2. So it uses up 3. So there's no feedback loop on that one. But we still want, because 2 come out, we still want to put those back in. At the same time, we have to feed some fresh U-238. And that's going to come in from belt here. So fresh U-238 comes in here. And then what's going to happen is we're going to read the contents. So it's got 9, right? We're going to run the wire to this belt. And we're going to say enable, disable, only enable when U-238 is less than, say, 5. So because it takes 5, so we got 4 in, and it's running, so it will allow 1 more, and that comes in, and it will stop. And then this, the waste, the extra 2 byproduct will come out this way and go into this belt. Not this one, this one. And then it will come out the other side where it gets picked up by this and put back inside. I don't need a wire on this. It'll always do it. And then so the first 5 will come in and get processed. Then 2 will come back out and they'll get put back in. And while the 2 are coming back out, 5 more will probably come in, making it 7, which is fine. But then this will stop until it's below 5. So I think this will work. I think this is fine. Man, that's not bad. All right, this is my prototype. Kovarex prototype. And of course, we would want to surround this with beacons and everything that we can to get as much as we can out of this one. Or I could tile it, which is perfectly valid. I mean, this whole thing can be copied. But it should be self-sufficient, and it should dump any excess over 40 into this chest, because it never needs more than 40 in the system. Great. Now, this has been running for a while. Let's just check the last hour, and you can see that it's solid. It's been 1.4 gigawatts very nicely. I love this design. I'm very happy with it. Oh, notice this is no longer flashing. It's interesting. 60 kilowatts. All right, I'm going to save this, and we will try making this in game because I think we're ready to enter the nuclear age. That's it for now. Thanks for watching. See you in the game.